Hi, my name is Laura Hensley,
I'm Olivia Raddick.
And I'm Braden Green.
and this is our Lab 5 presentation. The objectives of this lab include designing a speed controller, testing different kinds of controllers such as proportional integral controllers, proportional derivative controllers, and a hybrid of the two called proportional integral derivative controllers. Lastly, we had to take into consideration design specification given to us by Solco. The customer specifications Solco had for us included reaching a steady state speed of 12 radians per second, an overshoot/undershoot of less than 2%, which minimizes fluctuations when reaching the desired speed, a rise time greater than 0.1 seconds, and a settling time less than 0.2 seconds, allowing us to reach the desired speed at a comfortable acceleration while still ensuring reaching the desired speed fast. The amount of voltage used should be a lot less than 24 volts, as that could become dangerous during testing.
For the controller design process, we conducted several experiments. In the first two experiments, we developed a mathematical model to determine experimental parameters and constraints, like parameters of friction, damping, the motor torque constant. We also determined internal motor resistance, the EMF constant, the minimum voltage to spin the motor, the DC gain, and the time constant. The lab, after we determined all of these parameters, we used to model a controller and determine the necessary gain values that we needed to meet the customer specifications. In the lab, after we had determined all of these values, we tested the various types of controllers discussed earlier, like the proportional integral, the proportional derivative, and the hybrid controller. And we analyzed each of these controllers' results to determine which of these controllers would fully meet our customer specifications. In the final lab, we decided to use a proportional integral controller because it fit our specifications the best. We further constrained and tested this controller to meet those specifications. To finalize our controller design, we needed to more fully meet our specifications and to further constrain our controller. We also used various conditions to adjust these specifications. And some of those various conditions we put this under were a voltage disturbance to determine how the controller would react to these various sources of error. We wanted to determine all of the sources of error and problems this controller may face in reality and minimize those sources of error as much as we possibly could.
Here we have the results comparing the experimental and theoretical responses of our system using the PI controller. In both graphs, the system was given a desired speed of 12 radians per second, shown by the red line. As we can see, both the experimental, which is the purple, and theoretical, green, responses closely follow this input. The rise time is slightly over 0.1 seconds, which meets the customer's comfort requirement. It's fast enough for good responsiveness, but not too steep to cause discomfort or jerkiness. The overshoot is minimal, staying well under the 2% limit, which shows that the controller responds smoothly without large fluctuations. On the right graph, the system settles very quickly, well under 0.2 seconds, which means that it meets the requirement for fast but stable performance. Overall, the PI controller did a great job in both simulation and real-life tests. The close match between the theoretical and experimental results show that the system behaves predictably and reliably, even with real-world noise or small variations. For our final recommendation, we proposed using a PI controller. While PD was also considered, PI offered better long-term accuracy and reliability for our application. Starting with why. It eliminates steady-state error, which ensures the system constantly reaches the exact desired speed. It's also simpler to implement and tune than a full PID controller, which makes it ideal for practical, real-world systems. In terms of pro, the PI controller provides a smooth and stable response with no oscillations or instability, which meets the customer's need for comfort and consistency. It's also easy to adjust, requiring less trial and error during tuning. However, there's some trade-offs. The PI controller can introduce slight overshoot, meaning it may go up a little above the target before settling. And because it doesn't use the derivative term, it's best used in low noise environments, which signaling filtering isn't as critical. Ultimately, the controller is best suited for systems that require reliable, steady-state performance without the complexity of high-speed correction or advanced hardware. Examples include electric vehicle systems, speed control, home automation, and process control systems.
In the future, this controller design can be used for different specifications. We can change the specifications and further constrain our controller design. We have the ability, because of these experiments, to quickly change to a different controller, like a proportional derivative or a hybrid controller, in the case of extraneous limiting factors. We can further constrain the design to increase its efficiency and make it better for more tight specifications. And we can go beyond these small DC motors and go for larger DC motors or even change to AC motors.
Thank you for listening to our presentation.